Hello everyone and welcome to this tutorial. So in this tutorial I will do the MATLAB coding for backbar forward sweep power flow method in IEEE 33 bus system. So my previous tutorial was about the concept of backward forward sweep power flow method. And if you are not familiar with the backward forward sweep algorithm, I encourage you to watch my previous tutorial, which explains everything. So if you find this tutorial helpful, do not forget to like and subscribe to my channel. So let's get started. So here in MATLAB, I need to first create a new script. And yeah. So we always write three expressions at the beginning of our codes, which are CLC, clear O, and close O. And after that, we first need to load the data to our system. So in this tutorial, I will use the data for IEEE 33 bus system. And the data is available online. I will also show the data over here. And let's first define our line data, which is LD, and we are going to load it from another script which is titled line data 33 bus.m file, and we are also going to load our bus data. Bus data means the apparent power that each load absorbs from the system, and this is defined by BD, which stands for bus data. So let me just write definitions over here. This one is line data, and this one is bus data, and we need to change this one to bus data. Okay, so I actually have the bus data, and this is the line data for IEEE 33 bus system. And as you can see, these are the first column shows the line number. The second column shows the in bus, or the bus that is located at the beginning of the line, and the third column shows the bus that is located at the ending of a line, for example line 4. The beginning bus number is 4 and the ending bus number is 5. Or for example line 18, the beginning bus number is 2 and the ending bus number is 19, and yeah, that means that we have a branch going from the second bus to the 19th bus, and it creates the line 18. Okay, so the fourth column shows the data for resistance of each line, and the fifth column shows the data for inductance of each line. And also we have the bus data over here. Bus data consists of 3 columns, and the first column shows the bus number, which is maximum 33 buses, and the second column shows the P for the load connected to the for example second bus, and this third column shows the queue of the load that is connected to the second bus. Okay, so this is the bus number, this is the P of the load connected to that bus, and this is the Q of the load connected to that bus. Okay, so after that we need to transform our data to per unit values, and we need to define our base power and base voltage. So I'm gonna just write as base is equal to 100 megavolt, sorry, 100, which is indicated in megavolt amperes, and my base voltage is V base, which is 11 kilovolts. Okay, now I can calculate my base impedance, which is basically calculated by this expression. The data shown for the lines and for the bus data over here were not per unit. So now we are going to first transform the line data and line data. Only the fourth and the fifth column were the impedance data, so we are gonna write it like this. And the data for our bus was on the second and third column. Okay, now we need to define the maximum number of buses that we have in our system, and this is defined by n, and we write it like this: maximum of the LD in second or the third column, because that was the columns that we wrote the number of our buses, and we just defined each line is connected from which bus to which bus. And I think that's all. Okay, so after that we need to define the S of each load, which is basically the complex of the second and the third column of BD. And we define our initial voltages, which is defined by V, and we assume that all the bus voltages are 1 at first. This is equal to the size of . BD. And we need to write one here as well. Or you could just simply say ones for number of n. Instead of writing size BD, you could write n simply. That wouldn't make a difference. Let me also write here the definition: initial voltage values, and after that we define the z of lines. Z equals to the complex of the fourth and fifth column in our LD. Okay. And we define the line matrix. So we define it as zeros because we have no values for our line current at first. And this is equal to the size of the first column in LD. Okay. So this is current in lines. And we define the iteration number. For example, I want to repeat this for 2000 iterations. I think 2000 is more than enough. Usually the algorithm converges in less than 100 iterations. Okay, so we are going to start our main loop, which is our backward forward sweep method. So I'm gonna write here first we need to write the backward sweep, and it starts from here for I from 1 to the number of iterations, and actually I needed to write this inside for, because this is our main for. Okay, let me the algorithm. Okay, the backward sweep. As I said in the previous tutorial, we first need to calculate the current that is absorbed by each load, and this is defined by I load, and it is the conjugate of S load divided by our V. And after that we need to go back from the end of the feeder to the beginning of the feeder. So we write this for. So in this loop we are going to start from the end of the feeder, and therefore we are going to define it as J from size LD and 1, and go back to the beginning of the feeder. So I'm gonna write start from the end of the feeder. Okay, and after that we are going to define the C matrix and the E matrix. We will need these two matrices in future, so we gonna define them here, and we are going to write this, and I will explain what it means in a moment. So this is the end of the backward sweep. Let me explain from here where we left. So in here we define two matrices which we will need it later, and here we find all of the values in the second and the third column of the LD, which have the value equal to the line that we are assessing right now, which is LDJ3. And as you can see, for example, when the J is, for example, 31, it's going to find all of the values in the second and the third column of LD. For example, here you can see LD, okay? And here, let's see how many 32s we have. 31, I'm sorry, 31s we have. So we have 31 over here, and we have it also over here. So it's going to give us two column values and two raw values, okay? So the first argument here shows the row number of the all of the rows and columns in here that have 31 in them. That means it shows 30 and 31, these two values, okay? And the second one basically shows the column number, which is 1 and 2 in this code, and we are not going to need E anyway, so we are going to work with C over here. So after that, we say that if the size of C is equal to 1, the current passing through the J line is equal to the current passing through the corresponding load. What do you think this means? Okay, so as I mentioned in our tutorial, in the last bus, there is no further line connected to that bus, so the current passing through the last line is equal to the current passing through the last load. So this basically means that if the number of lines connected to this bus is only 1, then the current passing through this line is equal to the current passing through the load that is connected to the corresponding bus. Okay, so I'm gonna write a definition here. If C has only one value, that means J is a beginning or an ending bus. So for example here you can see that for 33 we have only one 33 over here, and that means 33 is an ending bus, okay? Or for example 18 is also an ending bus too, because it is only repeated once, and there is no other line connected to this bus except the line 17. Okay, if there are more than one line connected to the jth bus, and where that means else, then the current for this line is calculated by the corresponding load current, which means the load that is connected to the corresponding bus, and also the sum of the currents of all lines that are connected to the same bus as well. And since we calculate I line LD, J, and 1 twice in here, we need to subtract it once more over here. Okay, so note that this is because in C we have the J value as well. Okay, so we are basically just calculating it twice, and we need to minus that one time. So let's go back to the forward sweep, and I need to write an end here for that if. Okay, so the forward sweep and here we start from the beginning of the feeder and we go to the end of the feeder. Okay, so for J that is equal to 1 until the size of LDM 1, And this is basically the KVL method. And let me write the end for 4. Okay. And VLD JM3 means the ending bus voltage is equal to the starting bus voltage minus the line current, the line that connects these two buses to each other, multiplied by the impedance of that line. Okay, and that's all. That's all. Oh, we can also calculate the losses of the lines. Let me first divide voltage, magnitude, and angle. And after that we can calculate the losses. Their losses are basically P losses is equal to the real part of Z multiplied by the current times 2 . And Q losses is the imaginary part of this expression over here. And yeah, I think that should be fine. Let's run our script and see. Okay, so we first save our script, and I'm gonna just name this main and change the folder. We have an error. Yeah, I forgot to write the equal sign. So I forgot to write the equal sign, and let's run it again. And okay, I think it's fine. Let's plot voltage. So this voltage value, this voltage magnitude is not right. It should be in per units. So I have a problem in my data. Let's go back to our script. I think I did something wrong in here. Okay, so our base power is 100 megavolt amperes. Our base voltage is 11 kilovolts. Okay, so base Z is also this one. That's true. Okay. Okay, I see the problem. Here I should write. Okay, so this is 100 megavolt amperes, and the values indicated in BD, these are in kilowatts. So I need to add something here. Add a coefficient of 1000 in here to convert the megavolt ampere to kilovolt ampere. And yeah, I think this was causing the problem. Let's run again and see what happens. Okay, plot voltage. Yeah, okay, you can see the problem is fixed now, and my voltages are like this. you can see the angle or the power losses as well. Let's see how much power loss we have. P. This is the power losses in each line, and they are in per units, of course. That's why they are so small number. So that's all. Thank you for watching, and if you have any questions, please comment them below and I will answer them as soon as possible.